We're going to continue talking about thermochemistry today. Same big idea we indicated the other day, big idea 5. We're going to be using laws of thermodynamics to talk about the role of energy in chemical reactions. We're also going to be looking at whether a reaction occurs without any assistance, known as a thermodynamically favorable reaction. So we're going to continue with where we left off last time. We were talking about calculating heat transfer, where heat transfer Q is equal to mc delta T. What temperature does water boil at? 100 degrees Celsius. And that temperature remains constant. So what's the delta T when you undergo a phase change? 0. So if you plugged 0 into this equation, what must Q be? 0. But there is heat transfer when a substance undergoes a phase change, such as melting, boiling, condensing, or freezing. So instead of using this formula, chemists have derived 2 other formulas to calculate heat transfer when a substance undergoes a phase change such as boiling, freezing, evaporation, condensation, etc. We can calculate heat transfer in the following way. When a substance undergoes a phase change from liquid to gas, it vaporizes. And we can use the delta H of vaporization, which indicates the amount of heat that must be absorbed to vaporize 1 gram of a liquid. You'll use this for boiling and vaporizing. You'll use it for condensing as well, but whereas boiling and vaporizing are endothermic processes with positive Qs, condensing is an exothermic process with a negative Q. So the delta H of vape in that case would be negative to give rise to a negative Q. You can calculate it as Q is equal to the mass times the delta H of vaporization. In the first example, it says calculate the heat required to change an 120 gram sample of liquid ethyl alcohol, that's ethanol, into vapor at constant temperature. The delta H of vape of ethyl alcohol is 879 joules per gram. How would we calculate the heat required? What do we do? What do we do?
Mass times vaporization.
Exactly. Q is equal to the mass times the delta H of vape. We've got 120 grams times the delta H of vape is 879 joules per gram. Grams cancel. You're left in a unit of joules, which is a unit of energy. And you'd have 120 times 879. And at first glance, it appears to be this. We do want to watch our sig figs, though. You can do this, or this, or this. Any of those would be fine. Please remember that 1 kilojoule is 1,000 joules.
Dr. Karen, will it always give you the delta H of vaporization? Because like in honors we had it on our periodic table, but now we don't.
Right, so they will give you the value in the problem. The only thing I'm seeing is sometimes they're a little sneaky with the units, so really watch the units given, and sometimes you may be given kilojoules per gram or kilojoules per kilogram, and I've got a couple of examples there where you'll see the unit playing they're doing, and that way you'll be cognizant of it. The other thing I want to mention is if this was a part 1 question where you don't have your calculator, it would probably be like 100 grams. It'd be very easy non-calculator based math.
Will it ever be moles?
It can be, and I'll give you an example in a bit. But again, if you let your units drive your problem, you'll get there. Sort of like driving a car with directions or with a GPS. All right, try number 2. It says how much heat is released when 25 grams of steam at 100 degrees Celsius condense. Why would heat be released? It's condensing endo or exo? Exo, hence heat's released. What'd you get? What'd you get? Yes, yes? All right. So delta H of vape and delta H of condensation are equal but opposite in sign. Condensation's an exothermic process with a negative Q value. We have a different constant when you undergo melting, where the substance will change from solid to liquid. In this particular instance, we are going to have the delta H of fusion. This is the quantity of heat needed to cause 1 gram of a solid to melt into its liquid phase. You can use this for freezing or melting. Melting will have a positive delta H of fusion. Freezing will have a negative delta H of fusion. Multiply those two variables to calculate the heat transfer. How would we do number 1? You got it. So in this problem, we're going to have Q is equal to M delta H of fusion. And what we've got here is the mass is 25 grams. The delta H of fusion is 64.5 joules per gram. Grams cancel. We have 25 times 64.5. And in sig figs, that's going to be 1,610 joules. And you should try number 2. You've either got it in your notes or on your Chromebook. And you should have gotten this. Yes? Okay. Piece of cake. Now sometimes they do ask you to put the pieces together where you first melt a substance and then heat it. where you would be required to calculate both Q's and take the sum of the two. If a substance undergoes sublimation and you're not given a delta H of sublimation, you'd have to take the three pieces together as well. And we'll look at an example of that in just a minute. What I also want you to see is a heating curve to really link these concepts together. You have seen heating curves in the past, and what you're looking at here is the transition that the substance takes as it undergoes an increase in temperature. Temperature on the Y, time on the X. Here you've got solid water, so you've got ice. At 0 degrees Celsius, the substance melts and undergoes a phase change. Right here is where you would be looking at the delta H of fusion. You may want to indicate that on your graph. Water in the liquid state, and here water and steam coexisting at 100 degrees Celsius, where the substance is going to undergo vaporization. This would represent delta H of vape. And then finally, you've got water in the gaseous state, you've got water vapor or steam. Please note that the length of the plateau where the substance is vaporizing is considerably longer than that of the plateau length when the substance melts. Why might that be the case? What happens when a substance melts or boils? What gets broken? Bonds or intermolecular forces? Intermolecular forces. At this point, you don't have to break them all. Or you may break them, but some may reform. Here, you're going to break them all, and as those particles leave the liquid state and fly off into the gaseous state, they start to move fast, and there's no order. And as a result, no IMFs reform. So here, you're going to break them all, and it's just going to take a little bit longer. You will find that delta H's of vaporization are larger than delta H's of fusion because of this issue. If we go back into your notes on solids and liquids, shown here is a heating curve, and this one may be a little bit clearer than what I've shown you. Again, you can see that the length here is considerably longer than this one, even though both of them show a break. Please note that the energy that is added is used to disrupt the intermolecular forces for the case of water, hydrogen bonds, as well as dipole to dipole and London dispersion forces, and that is why you have a longer plateau length. You'll also note, and this may not be drawn that well on the image I gave you, perhaps I should insert this one in as well. You will note that the slope of this line is more severe than the slope of this line. As well as this one, and so you can see that in regard to the change in temperature over a shorter time span. So let's take a look at what happens when a substance transitions through different regions. And you're going to see a question such as this on your practice quiz, which you all have at this time. And if we look at that question, that's going to be in the first part 3. And let's take a look at question 6, which is right here. Is that better or worse with the box? Or it doesn't matter? Okay. It says 1 cup of ice has a mass of approximately 250 grams. The ice is at 0 degrees Celsius. How much heat is required to melt the ice and then warm the resulting water to 25 degrees Celsius? A table of useful information is provided. How do we approach this?
You start by multiplying the mass with the heat of fusion.
But you have to change the heat. You have to change the mass to kilograms.
Maybe, maybe not. Let's take a look. So what we have here is we've got a mass. I think I'm going to need more room. I'm going to flip. We've got a mass of 250 grams. Actually, there is no decimal there. I stuck it in, but it's not in the problem. The temperature of the ice is 0 degrees Celsius. We want to know the heat required to melt and warm. The final temperature is going to be 25 degrees Celsius, and some information is provided. So Sarah, what did you say we should do?
Multiply the mass with the heat of fusion.
All right, so the mass is 250 grams, and the heat of fusion is 332 kilojoules per kilogram. Do the kilos cancel?
Yes.
And now will the grams cancel? Okay. So we've got 250 times 332 is 83,000 joules, or 83 kilojoules, correct? Now what should we do?
Use the formula MC delta T.
Okay. Same mass. Specific heat is 4.18 joules over grams degrees Celsius, and delta T would be
25.
how do you get delta T?
Final minus initial.
Final minus initial. So 25 minus 0? Going to be left in a unit of joules. And now how will you get the total Q, if you will? Just add them together. Now we got 109 kilojoules. They offer up 110. Close enough. Not hard. You just have to read the questions carefully and plot out a good pathway to solve.
Can you go back to the question for a second?
It's right here. What's up?
I just wanted to see like how it phrased what it was asking for.
And they're very nice about it here, because it says required to melt and then warm, and they might not be that nice about it on game day, but we're going to take a look at that.
So the melting is the heat of fusion and the warming is specific heat?
You got it.
Will they always get us the specific heat of
They're going to give it to you. They might give it to you as 4.2. That's fine. 4.2 joules per gram degree Celsius. And don't be upset if it's kilojoules per kilogram degree Celsius, because you can just cancel the kilos. And just remember that 1 kilojoule is 1,000 joules. This was the problem on the 2015 exam. It was the very last question on the exam. When you take your exam in May, keep in mind on part 2 there are 7 questions, 3 long, about 20 minutes each, and 4 short, about 8 to 10 minutes. This would be a short question. Give it a shot. Be very careful with your units. It's written slightly differently than what you've seen before, but you can do it. Both of them. Both of them. You want to see what A is so far? is what I got for A. Again, you had to do the pieces and put them together. How'd we do with that? Yes, yes?
For the first key, why didn't you put it to 2 safely?
You could. You could go to 15. It doesn't matter. Yeah, I mean, this is a constant. Sometimes I go off what's given. Either way, it's fine.
So you can just exchange M for N.
In this particular instance, it works because if you look at the heat capacity they gave you, yeah, and like I said, if you let your units drive your problem, you knew you had to get to joules or kilojoules, and so that would drive it. Same thing here. And say it again. Is that better? And how'd we do with B?
How do we start it?
B's actually much easier than you think. They're basically telling you the delta H for that reaction is 1675, and for how many moles of aluminum would that be? Look at the balanced equation. Can't see. Pretty funny. It's in your notes though. For 2, right? And you want to make a comparison per 1 mole, correct?
So you divide by 2.
You got it. So you divide by 2 and you have this. And now it says, which requires less energy, recycling existing aluminum or extracting aluminum from aluminum oxide? Which requires less energy? Recycling. 25 or 26 kilojoules is less than that of 875.
Where'd you get the
from another problem.
so the delta H recycle? How would we know that from A that's recycling?
They told you.
You did?
Yeah.
Oh, this is.
You just have to read it. Look.
Can be recycled.
Look, look, look.
From scrap metal.
I know, we don't like to read. Aluminum metal can be recycled, or you can extract it.
Oh, I thought it was like irrelevant. I read it, I just thought it was irrelevant information.
It never is if they give it to you.
That's
Right?
irrelevant a lot of the time. Like,
Not irrelevant, but sometimes not utilized directly in the mathematical part of solving, but
sometimes you
always relevant.
sometimes you put like phosphorus is used in toothpaste, and we just don't need to know that.
Yeah, that's true.
Phosphorus and
I
toothpaste?
made,
No,
I made
no.
it. I made it up.
Ah,
Fluoride.
fluoride is relevant in toothpaste because that's what.
Yeah, but you didn't need it. It would be like
But that
fluoride.
has nothing to do with the
Fluoride.
problem.
Well,
Any toothpaste
it's just
contain
read.
fluoride
Yeah.
ions. Find the concentration of fluoride from this balanced equation.
Yeah.
But
Nothing
it
to
is
do with
important.
toothpaste.
Keep in mind they want every question to not just be in isolation. They want it to be relevant to what's going around the world, you know? Makes sense. All right. Pretty solid on Q calculations? Not bad. Here's the best part. I promise. Well, 2 best parts. Bomb calorimetry is no longer assessed, so we won't be playing with bombs. Probably safer. Last piece of the puzzle.
You can't do it live with the bottle?
No. Last piece of the puzzle in this chapter is Hess's law. Now, previously, we love Hess's law. Previously, when we calculated delta H, we could calculate delta H two ways. One was to use this formula that we introduced the other day, where the delta H is a formation of products taking the sum of all minus the sum of all the delta H is a formation of reactants would yield your delta H for the reaction. Another way that you have already been assessed, so I want to make this clear, we can do, as they suggested, taking the stoichiometric coefficients into account, and that's products minus, those are sloppy sigmas,
The first one's okay. The second one just looks like an E.
just get over it, silly goose. Happy?
That's looking up.
Perfect.
Golly.
It's
So
like your
silly.
art skills all over again.
I know. Alrighty. The other way you can calculate it is bond energy of the products minus bond. No, see, now you made me think silliness. What's wrong with that? When you do bond energy, you have to do what minus what? Reactant minus product. Don't confuse. Almost everything is product minus reactant, but bond energy is the opposite. Reactant minus product. Another way you can calculate delta H for the reaction is through Hess's law. The reason why you can do it is because enthalpy, as we've said, is a state function. It only depends on the beginning and the end. You can see this and this is a little bit tricky of a diagram. If you were reacting, look over here for a minute. Nitrogen gas and oxygen gas, you would generate nitrogen dioxide. If you had the delta H's of formation of all of them, you could do 2 times this one minus the sum of these delta H's of formation. Alternatively, you could do this in a multi-step process which I'll show you not with this example, but rather here. If we want to calculate the delta H of formation of this reaction here, if we have a series of reactions that when summed together equals the net reaction, we can sum their delta H's to get the delta H of this reaction. You would do this if you didn't have the delta H's of formation of each one. Not a difficult concept, just be very meticulous. Hess's law says that the heat of a reaction is constant whether it's carried out in one step or through a series of steps. And those series of steps you can see here. Instead of going from here to here, you go from here to here, then you go here, and then it's just the sum of the two. If an equation has to be reversed, and I'll show you when that occurs, you'll change the sign of delta H. If an equation has to be multiplied, you'll multiply the delta H by that factor. That multiple can be a fraction a 1, a 2, a 3, a 4, etc. It's not 0. In the first example shown here, I've got it worked out in a series of steps, and then we'll work through some on paper so you can see. It says use the following equations to calculate the enthalpy change delta H for the reaction in bold. This is the reaction we want the delta H for. I've set this up two different ways because if the numbers weren't that user-friendly on the AP exam, you would be more apt to see X's and Y's. Rather than going directly from nitrogen dioxide to dinitrogen tetroxide, we're going to take it in a series of steps. In the first reaction, we're going to generate dinitrogen tetroxide from nitrogen gas and oxygen gas. This is an endothermic reaction. In a second equation, we're going to react nitrogen gas and oxygen gas, and this time get nitrogen dioxide. If the sum of these two equations is equal to this, then this delta H is equal to the sum of these two delta H's. My approach to work these types of problems is to typically start with the first reactant. I've got nitrogen dioxide here. I look for nitrogen dioxide in one of the step equations, if you will, and I see it right here. The coefficient matches, but this substance is indicated as a product, where here it's indicated as a reactant. In order to sum those equations, I need to flip that reaction around, and when I flip the reaction, I change the sign for delta H. So product becomes reactant, reactants become products. I've changed the sign for delta H. Now I'm going to check to see if, when added together, those two reactions equal what I want. I also usually examine the product before I do that. The product highlighted in green is shown here. The substance is on the correct side and the coefficient matches. That's a good sign. I can sum those equations together now, and a couple points to raise here. The 2 moles of nitrogen dioxide drop down. I've got 1 mole of nitrogen gas on the left, 1 mole of nitrogen gas on the right. If you have the substance as a reactant in one equation, a product in the other equation, and the number of moles, that is the coefficient, is the same, it just cancels. Same holds true for the oxygen gas. I can sum these two together, and I get negative 24 kilojoules. If I just had X's and Y's, it would be X plus negative Y, because it's the sum of, or just X minus Y. Let's take a look at another one. For some of you, I know you remember this. It still requires practice. On number 2, I look at the first reactant. I see 2 moles of carbon as graphite. I see it right here. It's a reactant, which is a good sign, but what do I need to multiply that equation by? 2. When I multiply that equation, I put a coefficient of 2, 2, 2, and I multiply the delta H by 2, whatever the delta H may be. Oxygen's all over the place. I don't want to deal with it yet. I look at 2 moles of carbon monoxide. Where is carbon monoxide? On the other side. Does the coefficient match?
No. Yes.
Yes. So I don't have to multiply it, but what do I have to do to that equation? Flip it around. So I'm going to flip this equation, which is what is shown here. It's flipped here. And when I flip it, what do I do to the sign of delta H? I change it. So now it's positive because it was negative. Let's see if it adds up now. the graphite drops down. I've got 2 moles of oxygen on the left, 1 mole of oxygen on the right. It's like having 2x on one side of an equation and 1x on the other. You simply move the x to the side that already has more x's. All you have to do is subtract. 2 minus 1 is 1 oxygen on the left side. It's on the left side because you had more on that side to begin with. I've got 2 moles of CO2 here and here. That's going to cancel. A product on one, a reactant on the other with the same coefficient cancels. If you have substances on the same side of the equation, you just add them together. I add the delta H's together, or you can do negative 2x plus y. This third one, I'm not sure how your notes printed because when I looked at mine, I still had last year's work in it. Do you have the work built into it? I believe you do because I see colors. What you're looking at here, and I'll work through it. Again, best place to start right here. Where do you see propane? Right here. Coefficient correct? Yep. Is it on the correct side of the equation? Sure is. Oxygen's all over. I don't want to play with him yet. I've got 3 moles of carbon monoxide. Where's carbon monoxide? So I have to flip the equation, which means I have to change the sign. But what else do I need to do? So I'm going to flip the equation. Which means I need to change the sign. But what else do I need to do? I need to multiply by 3. So that's going to make 3, 3, and 3 halves. And I need to multiply this by 3. Let's see if it works now. I've got 4 waters. That's a good sign. Let's check out those oxygen. I have I have 5 oxygen here and 3 halves oxygen here. 5 is the same thing as 10 halves, right? 10 halves minus 3 halves would be 7 halves. And now I just sum this out. Yes, yes? Okay. So Hess's law, yep.
Where did the 3 halves, 3 over 2 oxygen come from?
Here,
Yeah.
initially it was 1 half, and when I multiplied by 3, I got 3 halves. Okay? Hess's law is another way to calculate delta H, and this all links enthalpy together. There are many ways to calculate enthalpy changes. Enthalpy is a measure of the energy content in the system at constant pressure. You also want to be able to link delta H to Q. What you're going to see in the lab is that delta H is equal to Q over the moles. So there will be a linkage with all. Some of you will be ready for this crazy hard problem. There are many other additional Hess law problems at the end of the chapter in your textbook to practice. This question here is difficult. Harder than anything you'd probably ever see, but if you can do it, you are in good shape. If you want to try something a little simpler, the one on the screen is a little bit easier to at least get going if you want to give it a shot.
Can we try the hard one?
You can try whichever one you want. We'll reveal the answers after the break. Questions on anything in chapter 6? All right, so this is the beginning in terms of thermo. You've got the thermochemistry piece. We're going to get the thermodynamics piece next.